Hey guys, welcome to Pre-calc Lesson 12.6. Today we're going to talk about discontinuity. So discontinuity, what is it? A function is discontinuous when the limit of f of x as x approaches c from the left and the limit of f of x as x approaches c from the right, and the function evaluated at c are not all equal. So two of the three can be equal, but they can't all be equal. So here's what we're talking about. Here's a limit from the left. Here's a limit from the right. There's the function. In this particular case, all three would be equal. So here's a picture of a function that is continuous. What we're talking about for discontinuity, not all three of those would be the same. So we'd have maybe a left-hand limit that looks like this. Maybe the function equals that. And there's my right-hand limit. So notice the function evaluated at c and the right-hand limit are the same, but not all three are. So here's a picture of something that is discontinuous. Now, we're not going to be drawing pictures for all these. We have to determine this algebraically. So there's different types of discontinuity, three types we're going to talk about. The first one is point discontinuity. Now, the nice thing about point discontinuity is it looks exactly like it sounds. Point discontinuity is a hole in the function. So visually, we have something that looks like this. There's some function, continues on to negative infinity and positive infinity, but there's a hole in the function. That's an example of point discontinuity. All right, so how do we determine that algebraically? Okay, let's take a look at this example. Where is f of x discontinuous, and what type of discontinuity is it? Well, right now we only know one, point discontinuity. But here's the key. To determine where something has discontinuity, you've got to look at that denominator. So when I see this, I'm going to think to myself, well, where is the denominator equal to 0? So I think it's pretty easy for you guys to see, well, when x is negative 4, that denominator is equal to 0. So that means I have discontinuity at x equals negative 4. So now, what do we do next? I know there's discontinuity there. What type is it? Well, after you determine where it has discontinuity, you have to find the limit at this value. So what we're going to do next is we're going to take the limit of f of x as x approaches negative 4. Now, f of x is this function right here. Okay, so what I want to do next is I'm going to take the limit of, and let's factor that numerator because maybe I can cancel something. So that's going to be x plus 4, x minus 2 over x plus 4. And as x approaches negative 4. Now I know if I plug negative 4 in right now, it does not exist. But remember some techniques for evaluating limits. Factor, then cancel. So what happens now, this and that cancel. I plug in a negative 4, and I get negative 6 for my answer. So what does this tell me? This tells me that it's discontinuous at negative 4, but the limit exists. So I've got a picture that looks like this. The limit exists. So coming from the left and coming from the right, you're pointing at the same value. That's a negative 6. But the function does not exist there, so I have a hole in the function. That particular coordinate is negative 4, negative 6, because remember, the limit is the y value, and where we're taking the limit there is your x value. So what we say is, as x approaches negative 4, the y value is going to be negative 6. So how do we describe this? We say it has point discontinuity, and we're going to describe it by saying there's a hole at negative 4, negative 6. And that's how you answer the question. Our next type of discontinuity is called jump discontinuity. Jump discontinuity is a gap in the function. Now, this happens in piecewise functions, but it doesn't mean all piecewise functions have jump discontinuity. But you see jump discontinuity in piecewise functions. So let's take a look at an example here. Where is f of x discontinuous, and what type of discontinuity is it? So the first thing I want you to notice are the pieces of the piecewise function. This top piece here, x squared minus 5, is simply a quadratic. So it's a parabola by itself that is continuous, no discontinuity there. The second piece, x minus 1, that's linear, a line, no discontinuity there. So individually, neither piece has discontinuity. Well, that's important because if this function has discontinuity, the only place it will is right here at 2, because that's where it switches from your quadratic to your linear. So how do you determine if it does? Well, what we are going to do is we are going to start by taking the left-hand limit and the right-hand limit. So here's what the left-hand limit is going to look like. I'm going to say the limit of f of x as x approaches 2 from the left, because we said, well, that's the only place there's going to be discontinuity. Now, how do you take a left-hand limit of a piecewise function? We have to think about what a left-hand limit means. That means you're coming from the left. So you're coming from negative infinity to 2. So we're not going to pay attention to brackets or parentheses. For a left-hand limit, you go from negative infinity to 2, which means I'm plugging into that function right there. Okay, so what does that give me? X squared minus 5, that's going to be 2 squared minus 5. 4 minus 5, that's negative 1. Okay, now what I'm going to do is I'm going to take the limit of f of x as x approaches 2 from the right. So again, I'm not going to pay attention to brackets and parentheses. I'm thinking to myself, the limit from the right. So this means we're going from infinity to 2. So that means I have to use this piece. Well, that's going to be x minus 1. So x is 2, 2 minus 1, that's positive 1. So what do we notice? I'm going to use that abbreviation that the calc teachers don't like. The left-hand limit does not, the left-hand limit does not equal the right-hand limit. So basically I've got this situation here. The left-hand limit's going to some value, the right-hand limit's going to some value, but they're not the same. So you can see right here, this is your gap. Okay? So how do you answer the question? Well, we call this jump discontinuity. Graphically, what does that mean? That means we have a gap from where to where? Well, we found both limits, all right? So what I'm saying here is as I approach 2 from the left, the y value points to negative 1. So there's 1 point, 2, negative 1. Well, in the other one, I approach 2 from the right, and that y value is 1. So there's a gap in the function from 2, negative 1 to 2, 1. And this is how you would answer that question. Okay, our third and final type of discontinuity is called infinite discontinuity. Infinite discontinuity is a vertical asymptote. Well, how do you determine if a function has infinite discontinuity or a vertical asymptote? We actually talked about this way back in lesson 12.1b, I believe. You're going to take a look at the function and first of all, figure out where it has discontinuity. So we talked about this. Discontinuity is where the denominator equals 0. And when we first talked about this in lesson 12.1b, we said, oh, these are always asymptotes. And I said, well, later on, when we get into limits, they're not necessarily always asymptotes. So I'm going to say now, where is that denominator equal to 0? Well, that's when x is equal to 4. So I'm going to say it has discontinuity at x equals 4. Well, now what do I do to determine what type of discontinuity is it? Is it an asymptote, or maybe is it point discontinuity? Well, what comes next is the limit. So I'm going to take the limit of f of x as x approaches 4. Well, if you notice here, I can't simplify this. I can't factor and cancel. So my only option to find that limit is direct substitution. Okay, well, let's plug in a 4. What happens? I get 4 over 4 minus 4, 4 over 0. That limit does not exist. So what do we know? We know that it has discontinuity. The limit does not exist. So visually, I'm going to have something that kind of looks like this. Okay, so I'm going to say that's a vertical asymptote. I have infinite discontinuity. That means I have a vertical asymptote at x equals 4, where the limit does not exist. That is your vertical asymptote. So there are the 3 types. We've got point, jump, and infinite, and they represent something different graphically. So now what we're going to do is let's put it together, see what happens. All right, so for each of the following functions, determine where it is discontinuous, what is the type of discontinuity, what happens at this place on the graph. Okay. Where does this have discontinuity? Denominator equal to 0. I don't think I need to write it out. As you guys can see, it's pretty straightforward. This has discontinuity at x equals 2. Now, it's not piecewise, so I'm pretty much going to rule out jump discontinuity. Does it have point discontinuity or infinite discontinuity? Well, what do you do next? You take the limit. You take the limit where it has discontinuity. So that's going to be as x approaches 2. Okay, the limit of f of x as x approaches 2. Well, f of x, what I try to do next is factor and simplify. But again, take a look here. I can't factor and simplify. So all I can do is direct substitution. 3 times 2 plus 1 over 2 minus 2, 7 over 0. That limit does not exist. So how do I know what type of discontinuity it is? Well, it has discontinuity. The limit does not exist. Anytime we see that, that's infinite. So I'm going to say this has infinite discontinuity. That means I have a vertical asymptote at x equals 2. So I've determined where it has discontinuity here, answered that part of the question. I've taken the limit. Since the limit did not exist, that told me it had infinite discontinuity. And graphically what happens? Vertical asymptote at x equals 2. All right, how about the next one? Okay, so again, what I'm going to look at here, where does it have discontinuity? It has discontinuity when x equals a value that's going to make this 0. Okay, so has discontinuity at x equals negative 2. So now what do? Now I'm going to take the limit as x approaches negative 2 of that function. Well, this one, it looks like I can do something with. All right, so maybe I'll try factoring that numerator. Looks like I can take out a GCF of a 2x, and I have an x plus 2 left. My denominator is x plus 2. So what I can use to evaluate the limit now is just this. Okay, plug in a negative 2. 2 times negative 2 is negative 4. So what are we saying? We're saying that it has discontinuity, but the limit exists. So visually, here's what we're saying. The function doesn't exist, but the limit does. Well, that looks like a point, so we call this point discontinuity. Point discontinuity, which means I have a hole in the function at negative 2, negative 4. So just a quick sketch graphically. Negative 2, negative 4. The function doesn't exist, but the limit does. Okay. So right away, example 6. I'm guessing jump discontinuity. It doesn't have to be. This could actually be continuous, or it could even have point discontinuity. And we'll get into that in a little bit later. But let's just take a look at each piece. This piece here is linear. Individually, no discontinuity. There's a quadratic. Individually, no discontinuity. So if this piecewise were to have discontinuity, it's got to be at 0, where it changes from one to the other. So what I'm going to do is I'm going to take the limit of f of x as x approaches 0 from the left. And again, if your piecewise function is written in, I guess, what I would call standard form, up at the top, we go from negative infinity to some value. This is the left-hand limit, coming from negative infinity to a number. So that means I'm going to plug into this. Again, don't pay any attention to brackets or parentheses when taking a limit. I have to go that direction, so it's going to be 2x plus 1. All right, 2 times 0 plus 1, that's 1. Okay, so now what I'm going to do is I have to take the limit of f of x as x approaches 0 from the right. And again, ignore parentheses and brackets. From the right means from infinity to 0. So I have to use this. That's going to be x squared. Okay, well, 0 squared equals 0. So what I'm saying here, the left-hand limit and the right-hand limit are not equal. So when those limits are not equal, the limit does not exist, and this has to be jump discontinuity. Which means graphically I have a gap from this coordinate here, 0, 1, I'm going to write that down, 0, 1, 2, 0, 0. Where does that come from? Here. All right, one more. All right, so this one is probably the most work of the ones we've done so far. First thing I need to do is determine where it has discontinuity. So that's simply going to be denominator equal to 0. Those are the places that has discontinuity. First thing I want to do is factor this, right? This factors pretty easily. X plus 7, x minus 2. And I think it's easy to see that I have discontinuity at x equals negative 7. I'm going to write over here, and you'll see why in a second. I also have discontinuity at x equals 2. So there's two places that I have discontinuity. When x is negative 7, because that'll make this 0, and when x is 2, because that'll make that 0. So what comes next? Well, I got to take the limit. Well, if there's two places where we have discontinuity, that means we have to take two limits. This one's going to be the limit of f of x as x approaches negative 7. And over here, I've got the limit of f of x as x approaches 2. So now, what I'm going to do here is, I notice I already factored it, so those cancel. So I've got this expression here that I can use to evaluate my limits. 1 over x minus 2. I'm going to use that here. I'm going to use that here. Okay, so 1 over x is negative 7 minus 2. That's 1 over negative 9. So what I'm saying here is that the function has discontinuity, but the limit exists. The function does not exist, but the limit does. So that's what it looks like, a hole in the function. So over here, this is what we call point discontinuity, which means we have a hole at negative 7, comma, negative 1/9. Okay, well, let's go to the other side. I'm going to use this function in this limit. Okay, 1 over x minus 2 is going to be 1 over 2 minus 2. That's 1 over 0. That does not exist. So now what I'm saying is the function doesn't exist and the limit doesn't exist. That's going to be something that looks like this. Okay, we call that infinite discontinuity. So I'm going to say infinite discontinuity. What does that give us graphically? A vertical asymptote at x equals 2. That comes from this right here. Okay, so pretty challenging lesson. Please go back, rewind it. Maybe work out some of the examples on your own before you look at the solutions again, just to kind of make sure it sinks in. And as usual, guys, if you have any questions whatsoever, please don't hesitate to reach out to myself or Mr. Ward. Thanks.